Welcome to Crystal Clear Chemistry channel. In order to crack either JEE mains or the NEET exam, let's strengthen our basics of chemistry through this channel. And in this video, I am going to start the organic chemistry part by part, and let's make the organic chemistry easy by knowing the fundamentals very clearly and whatever the concepts are needed in order to solve the problems that are given in the mains or NEET. I'm going to explain in detail. Believe me or trust me. Um, if you are very thorough about the basics or the fundamentals of organic chemistry, no doubt we can solve or we can answer any level of organic chemistry questions. We definitely we need to be very thorough about the organic chemistry, and of course practice also required for this organic chemistry, and it involves both by memory based questions, and it involves even the logical questions. So that is the reason why most of the students are feeling difficulty in dealing with the organic chemistry, but it's very easy. Let's make the organic chemistry easy, and I'm going to discuss the important topics and all in this channel. Stay tuned to this channel. Okay, right. What is organic chemistry? Organic chemistry is the branch of chemistry that deals with the carbon compounds. So we can say that organic chemistry is nothing but a study of carbon compounds. Study of carbon compounds. Except the carbides, bicarbonates, and carbonates, the carbon compounds with oxygen, hydrogen, sulfur, chlorine, bromine, etc. all comes under the organic compounds. We call the carbon compounds as organic compounds, and we are going to study those organic compounds, their preparations, properties, applications, and the reactions, etc. under this branch organic compounds. Till today, trillions of carbon compounds we know, and all these organic compounds are obtained from the living organisms, especially the living organisms. Study of these organic compounds started earlier around 1750 itself. We started the organic chemistry as a study of organic compounds earlier around 1750 itself, and after around 20 to 25 years, Berzelius was the first scientist who proposed a theory on the organic compounds called vital force theory. After studying the organic compounds that are obtaining from the living organism, and scientists were wondered how many compounds are there of the carbon, and how they were naturally obtained from these living organisms, and why only the carbon is forming the organic compounds and all. And Berzelius proposed that there must be some mysterious force which is called a vital force, which is responsible for the formation of these organic compounds. And he even proposed that we can't synthesize the organic compounds in the laboratories. Of course, later it was rejected. After the synthesis of the first organic compound, urea, from the inorganic compound called ammonium cyanate by the scientist Holler in the 1828. Ammonium cyanate, NH4CNO. After heating, the ammonium cyanate undergo rearrangement and readily produces the first organic compound, nothing but urea, with the formula NH2CONH2. This is the organic compound urea, and it was synthesized from the ammonium cyanate by the Holler in 1828. Thereafter, the scientist attempted to synthesize the organic compounds, and many of them were very successful. So, the Berzelius vital force theory was rejected, and the first scientist was the Holler, who synthesized the organic compound. And the second compound, or you can say the first organic compound which was synthesized from its constituent elements, is nothing but acetic acid, synthesized by the scientist Kolbe in 1845. Constituent elements means what? If we consider the acetic acid, which the formula CH3COOH, the elements that are present in the acetic acid are nothing but carbon, hydrogen and oxygen. Just from its constituent elements, he was able to prepare the acetic acid, and it through the electrolysis, and which is called Kolbe's electrolysis, and he was able to uh, synthesize the compound CH3COOH. And if we consider the next compound, around 1856, the scientist Berthollet prepared a gas called marsh gas, which is called methane, with the formula CH4 from the inorganic constituent elements, nothing but carbon and hydrogen. So, like this, there were many attempts, and now as on today we are able to synthesize the most complex organic compounds also, which are nothing but the medicines, dyes, paints, oils, etc., that are synthesizing in the laboratories or in the industries in the large scales. All those are nothing but the organic compounds. Okay, now if we consider the compounds of carbon and hydrogen, they are nothing but the hydrocarbons. The major sources of these hydrocarbons are nothing but coal tar and petroleum. If we consider the petroleum products, it contains a large number of hydrocarbons, both aliphatic hydrocarbons and aromatic hydrocarbons, which are very useful for our daily life. And if we consider the atoms like oxygen, nitrogen, phosphorus, sulfur, chlorine, bromine, etc., they also be they are the part of the most of the organic compounds, and they are called heteroatoms. So not only with the hydrogen, even the carbon, even with the oxygen, nitrogen, phosphorus, sulfur, etc., carbon can form a large number of compounds. All these organic compounds, as we discussed already, are obtained from the living organism, and which are nothing but the carbon compounds, and those compounds which are obtained uh, from other than the living organism are called inorganic compounds, and study of inorganic compounds as a separate branch called inorganic chemistry. Okay, now let us see why only the carbon forms a large number of compounds. If we consider the bond energy, the bond strength, no doubt the smaller atoms form strong bonds. Smaller atoms, if we consider the second period, among the second period elements, the carbon is having the highest bond energy with 85 kilocalories when compared with the other elements like the next period elements, or the nitrogen of the same period and all. If we consider, carbon carbon bond is so strong among the smaller atoms. Due to this reason, it can even form a it can even link with another carbon atom, it can even link with the another carbon atom and form a long chain compounds. This self-linking property of the carbon is nothing but the catenation. So because of this catenation property, the carbon able to form straight chain compounds or branched chain compounds, or it can even can able to form the cyclic compounds, ring chain compounds, etc. Large number, huge number of straight chain, branched chain, cyclic compounds, and the complex steroids, complex organic compounds are formed by the carbon because of this catenation. And not only this catenation property which is responsible for forming these many compounds, it is of the ability to form the multiple bonds, it is the ability to show the isomerism by the organic compounds, and no doubt it is because of the tetravalency of the carbon atom. What is this tetravalency of the carbon atom? If we consider the carbon, the configuration is 1s2, 2s2, 2p2 with the atomic number 6. 2s2, 2p2 means we know there are 2 electrons in the 2s subshell and sorry for that, yeah, 2 electrons in the separate p orbitals. And in the excited state, in the excited state, the excited state energy is around 120 kilocalories, and with the help of that 120 kilocalories the electron able to jump to the 2p orbital, so that it there will be 4 unpaired electrons in the carbon atom in the form of 2s1 and 2p3. Okay, so if we consider these electrons as they are unpaired electrons, they are ready to combine to get the toxic configuration and hence can form covalent bonds. So through covalent bonds, the carbon can form a large number of compounds through the self-linking property called catenation. And it can form the multiple bonds, it can form single bond, it can form double bond, or it can form a triple bond. And remember, definitely carbon in its compounds should have 4 bonds. That's why we need to write the carbon always with the 4 bonds. We need to always represent the valency of the carbon as it can form 4 bonds. We can say it has the tetravalency, and as it can share a 4 pair of electrons, we can say that the covalency of carbon is nothing but 4. Okay, now the carbon compounds can exhibit even the isomerism also. What is meant by isomerism means the compounds, two compounds, for example, if we consider a simple example like CH3, CH2, CH2, CH3, let us consider a compound which is called butane, and we have the other compound also which is called isobutane. These two are having the same molecular formula and they have the same molecular mass also, but they differ in their physical and chemical properties, and those compounds are said to be isomers, and that phenomena is called isomerism. As a separate topic we are going to discuss about the isomerism anyhow, but here the major 4 factors that are responsible for the formation of large number of compounds are nothing but the one and only one condition, one reason, if you want to say, it is of bond energy. The bond energy of carbon is very high, and the next extended factors are nothing but this catenation, tetravalency, multiple bonds, and the isomerism. Okay, more about this we are going to discuss in the coming videos. Now listen carefully. As the carbon can form a single bond, double bond and triple bond, we already know from the chemical bonding chapter. Uh, if we consider the compounds with the single bonds, compounds with the single bonds, the carbon can undergo sp3 hybridization. If the carbon has a one double bond, we can say it undergoes sp2 hybridization. If the carbon contains a triple bond, we can say that it undergoes a sp hybridization. As we know already about the hydrocarbons, the compounds of carbon and hydrogen, they are all of three types, majorly three types. They are nothing but alkanes. Alkanes, if the carbon atoms form only single bonds in the compounds, in the hydrocarbons, they are called alkanes. If at least one double bond is there, then it is called then those compounds comes under alkenes. And if we consider the compounds with triple bond, they are called alkynes. So, carbon shows tetravalency in its compounds. It undergoes different hybridizations in alkanes sp3 and in alkenes sp2 and in alkynes sp hybridization. Okay. Uh, if we look at that pi bond formation, carbon-carbon double bond shows one pi bond and carbon-carbon triple bond shows two pi bonds. Okay. Now listen here. As we discussed already, why carbon forms large number of compounds? It is just because of the catenation property. What is catenation property? It is nothing but ability to form the straight chain, branched chain and ring structures, as the CC bond is very strong, right? Now, what is the scope of this organic chemistry? It has a wide number of applications: pharmaceuticals, drugs, petroleum industries, dyes, foodstuffs, and whatever the compounds that we are extracting from the plants and the animals are of organic compounds. And for our comfortable life, we are using them in our daily life, right? So let's study. It's very interesting to study these compounds, and but the one and only one condition is you have to prepare or you have to practice every day to to bring that grip in that organic chemistry. Okay, to have that grip in the organic chemistry, you have to practice, and of course first you need to understand why, how, and in what way the reactions are happening, and how we are synthesizing, and why the organic compounds are showing some particular physical properties, some particular chemical properties and all. We need to focus. Okay, let us see how to represent the organic compounds now. Structural representation of organic compounds. Total we have three types of representations. They are nothing but complete structural formula, condensed formula and the bond line formula. The structural representation. Now listen carefully. Suppose if we consider a compound with the formula C2H6, as there are two carbon atoms, definitely there must be a bond between those two carbon atoms first of all. So let's write a bond here. Then, as I said already, definitely it should have four bonds. Every carbon should have four bonds in the organic compound. Apart from two carbon atoms, there are six hydrogen atoms. So share it equally to the two carbon atoms. So three hydrogens for each carbon atom. That means it can form a three single bonds with three hydrogen atoms, as the hydrogen cannot form any double or triple bond. Simply we write a single bond between the carbon and hydrogen. And for this carbon also we can write CH, H and H. This is the complete structural formula of a compound. What about the condensed form? It's known, it's not needed to represent all the bonds that are present in the compound. Let us write the short form of this complete structural formula. If we consider this particular part, this is nothing but the CH3. So CH3 we can write. Some bonds we can miss. That's why we did not write the carbon hydrogen bonds here, and this particular part also CH3. So you can write the C2H6, which is called ethane formula, as a CH3CH3, which is called condensed form. Okay, now suppose if we consider a compound with uh, more than one group, similar group. For example, if we consider CH3, CH2, CH2, CH3, we can just write that CH3 and the CH2 as twice CH3. This is how to write the condensed formulas. Okay, and let us see what about this bond line structural representation. We are going to represent the bond as a line. So whenever line is there, according to the organic chemistry, it is a bond, and whatever the edges or the corners are there for that particular line, they are nothing but the carbons. And of course the hydrogens atoms are invisible here. Invisible here. We don't write hydrogens, as we know already the carbon can form four bonds. When it is forming one bond with the other carbon atom, definitely the other three must be with that of hydrogens. That's what this bond line structural representation is all about. So suppose if we consider now the ethane, as there is a bond between the two carbon atoms, we are just representing with the line. As there are only two carbon atoms, we just left the two corners, represents two carbon atoms, and no need to write these hydrogens, because it is obviously uh, noted that the carbon can form four bonds, and hence the remaining three bonds must be with the hydrogen. Understand or not? Let us see another example here. For example, if we consider this particular case, there are four carbon atoms. So four corners or four edges must be there while writing. So let us see, 1, 2, 3, 4. Four corners represent the four carbon atoms, and there are three bonds between the carbon atoms. Those three bonds, CC bonds, are nothing but this particular first bond, second bond, and third bond with the line. Of course, we don't write the hydrogens, right? So here, if here this is the carbon, means definitely three hydrogens must be there. This is the carbon already with the two bonds, hence only two hydrogens. This is the carbon already with the two bonds, hence with the two hydrogens. So this is the first carbon, second carbon, third carbon, and fourth carbon. And if we consider the fourth carbon, as it combines with only one carbon, we can say there are three hydrogens that are invisible at that particular dot. So this is the bond line representation of organic compound. Okay, now, so what is complete structural formula? Two electron covalent bond can be represented by the dash. A single dash represents a single bond, and double dash represents a double bond, and a triple dash represents a triple bond. And the lone pair of on the heteroatom may or may not shown here. If we consider these structures, ethane, ethene, ethyne, and methanol, if we consider, you can clearly see all the bonds were represented, and here there are lone pairs on the heteroatoms like oxygen. We may or may not represent, but still this is a complete structural formula of the compound methanol. What about the condensed structural formula? As we discussed already, we can omit some or all the dashes representing in the covalent bond, and by indicating the identical groups attached to an atom by a subscript. Subscript in the sense, as we discussed already, if the compound contains 6 CH2 groups within the structure itself, no need to write all 6 CH2s. Simply by using the subscript, you can represent. Okay, and here no need to represent the single bond here, and we just simply represented the double bond here between the CH2 which is called ethene. Okay, now let us see what is bond line representation. Carbon and hydrogen are not at all shown in this particular representation. The lines are representing the CC bonds which are drawn in a zigzag fashion. Only atom written is heteroatom. Heteroatoms like oxygen, sulfur, chlorine, bromine, etc. are shown. And the terminals denotes the methyl group unless indicated with the functional group. And the line junctions also denote the carbon atoms which are bonded to the appropriate number of hydrogens required to satisfy the valency of carbon atom. That's what, as the carbon can form a 4 bonds, based on that we can able to write the, or we can able to predict the number of hydrogens that are attached to that particular carbon if they don't mention the hydrogens. Okay, so you can clearly see here, see this particular CH3 is this one and this is CH2. If we consider the CH as it is attaching with that of 3 carbon atoms, this is the junction carbon with 3 carbon atoms, and only one hydrogen will be there. And as there are 4 CH2s, we can clearly see the 4 CH2s here, and the final terminal carbon will be methyl group, and this is nothing but CH3. Here we need not to represent that CH3 also. But we need to represent the heteroatoms like bromine like this. Okay, now see, even the cyclic compounds also we can see here. This is the cyclic compound closed figure, or you can say closed structure or the cyclic structure, and you can see clearly the bond line structural formula for this. Okay, so you can expand. These are the some of the compounds for which they are asking us to write the expanded forms. Okay, now let us see how we can represent the organic compound in a 3-dimensional way. For a sp3 hybridized carbon atom with all single bonds, the bonds are represented with the normal line. And if we consider the carbon and 2 of the bonded atoms here, the hydrogens are in the same plane, and whatever the dashed wedge we see here, this is a dashed wedge is away from the observer, projecting away from the observer, and out of the plane towards the observer is represented by the solid wedge. This is the solid wedge, this is the solid wedge, and this is the dashed wedge. If H is in this particular screen plane and we are watching this hydrogen, this is towards the observer and this is away from us, that means away from the observer, below the plane of this particular screen, must be represented with that of the dashed wedge. Okay, this is how to represent the organic compounds.